We are going to talk about the temporomandibular disorder and its relationship with trigeminal nerves. And is it the one that we should blame for the pain condition and temporal mandibular disorder? Now, okay, so this temporomandibular disorder term is a collective term that can contain all the conditions that affect muscles and that are in temporomandibular joint or mastication or are narrated by a trigeminal nerve. And the statistics is that 5 to 10% of Canadians are affected by TMD, and in the world it's 3 to 12%. So in the orofacial pain conditions is the most common pain, chronic pain condition, and it has like high frequency. And the characteristics of it is that it has a spontaneous pain that comes upon the function like chewing and talking and yawning or wide opening of the mouth. And we don't know much about the pathophysiology of it and their lack of pathophysiology-based diagnosis, and we don't have much of effective care. It's just palliative care to help patients go through their painful episodes. So for studying this situation, genetics have been come to the help. There are studies like named GWAS, which is short for Genome-Wide Association studies that are hypothesis-free methods that look for a million variants of genes in the entire genome that are highly associated with a phenotype. In our case, the phenotype is TMD, and my supervisor previously has combined all 4 GWAS studies that are based on clinically verified TMD cases, which high number of cases, around 2,000, and 3,700 of controls. So what they found is that there have been 16 genetic variants that are highly associated with risk of having TMD. And this gene is located in somewhere in nowhere, middle of nowhere. However, this gene encodes a member of M14 protein that is a family of metacarboxyl peptides that are precursors of the protein that have roles in neurotrophic factors or promotes the neural survivals or shaping the neurotransmitters and everything. But if you look at the genetic variants close to this location, sometimes they're usually studied together as they have effects on each other. And these genetic variants here do not have any modification on nearby expression in dorsal root of ganglia, or does not modify expression of any genes in the inferable, meaning to pain in any pain-relevant tissue. So in some genetic studies, we look on the genes in the largest scale analysis that is related to the phenotype. So in this case, you might end up looking at biological pathways and its correlation to a phenotype, which is in our case is TMD. And we have several levels that I'm going to skip here because of our time. And in our case, we have found two biological pathways that are highly associated with risk of having TMD. And these biological pathways are related to semaphorin, plexin, and neuropilin protein networks that are empirical roles in morphogenesis of neural tissue, including trigeminal nerve. And well, alternation in trigeminal system morphogenesis can lead to morphostructure abnormalities in this nerve. And therefore, there will be facilitation of painful TMD. So it increases the risk of TMD. So what do we know till now in human basis? So brain imaging techniques have helped us to have some ideas about generation of white matter metrics. We use DTI techniques that will help us to track the white matter in the brain. And we previously had a problem with tracking this trigeminal nerve. Doing track symmetry in DTI for trigeminal nerve was not possible before, but we have a collaborator in the University of Toronto that has been helping us. So what is our main aim in this project is to first outline the tract and connectivity of trigeminal nerve through the face in coming out of the nerve stem to the face and the coming into the nerve from the brain stem. And that would help us to find the normal trajectory and connectivity in this nerve and compare it with TMD patients. So we have a preliminary data that shows that there is a difference between control and patient cases in connectivity and the trajectory, both in coming and going tract in the nerve in patients and controls. So if you see here, you can have a look. The red is our patient population, the green is our control population, and can see less connectivity in patient population compared to control. So our preliminary data then shows that there's a difference in central trajectory of CNV in patients and in peripheral in both preliminary data. And here we have done some analysis for quantified tractography. It also shows the difference between control and TMD. That here we can see that the connectivity has been reduced compared to control. So this also shows that we have reduced number of connectivity in patient population compared to our control. So we are going to move on with that with a higher number of patient and control subjects. And we have a second aim that in this aim, we are going to assess morphostructural abnormalities in trigeminal nerve in sensory pathways that leads to orofacialpain in mice. This is going to happen in our collaborator's lab, Dr. Sharif. And I'm just going to skip about this because I have not given enough time to just go through it as much as I could. But the short preliminary data has shown that suppressing semaphorin signaling in nociceptor events by half is enough to increase symptoms of both axial and radiating low back pain. Well, so what we're gonna have in our discussion is that the difference in the central and peripheral trajectories of CNV and TMD patients compared to the control. And then the CNV of TMD patients have a reduced number of connections into the brainstem and towards the face compared to the control. And also preclinical data shows that suppressing semaphorin signaling increased pain sensitivity in mice. So we might have the same situation in mice about trigeminal nerve that we had in low back pain. So the question still remains that is the trigeminal nerve the one to blame for TMD? We are still ongoing on this project. So hopefully we'll get into the direction. And thank you for listening to me. And for this project, we have Dr. Meloto's lab and Dr. Steve Moayedi in University of Toronto, and Dr. Luda Dichenko. And thank you for all.